Hello and welcome to the second of our 8-week webinar series, Advancing in Predictive with Alteryx. Today we will be covering logistic regression. Kind of just as an overview before we get started, here are the upcoming dates for the rest of our webinars. And all these webinars will be on Thursdays at 12 p.m. And a few notes before we get started, this webinar will be recorded and the link will be available via email before the end of the week. And we will also have a short Q&A session at the end, but you are welcome to go ahead and put your questions in the Q&A panel as we go along. And additionally, there will be some files that Kyle will be kind of walking through as he does this webinar, and I'll be posting that in the chat box of this webinar for you to access as well. And so a few introductions. My name is Rachel Mason, and I'm the marketing specialist here at Teknion Data Solutions, and Teknion is happy to be hosting this webinar. And then this webinar is being led by Dr. J. Kyle Roberts, who is our data scientist here at Teknion Data Solutions. A little bit about Kyle: he has held several professor positions at Southern Methodist University, Baylor College of Medicine, and the University of North Texas. He also co-authored the Y-HAT package in R, and he is an expert in multi-level modeling and co-authored the Handbook of Advanced Multi-Level Analysis. So at this time, I'm going to hand it over to Kyle.
All right, thanks, Rachel. Well, hey, we're excited to be with y'all again. And so if you haven't seen the linear regression webinar that we did last week, I encourage you to go to the Teknion website and you can download that. And so that will probably be a little bit helpful in understanding what we're talking about today with logistic regression, and then also using all of the tools. Also, as Rachel said before, let me strongly encourage, if you have questions, please throw those up in the chat room, and then we'll try to address those. And also, I think Rachel is going to throw up the web address where you can download files if you want to kind of follow along as we go, or if you want to do it afterwards. I'll try to go slow enough while we're clicking through things that if you are following along on your own computer, you can actually do that. Okay, so logistic regression. So let's talk a little bit about what we're doing in logistic regression. And so if we are in linear regression, last week we said that linear regression answers the question: as one variable of interest goes up, what does the dependent variable or the outcome variable tend to do? So in the case of let's say GPA and SAT scores, as GPA goes up, the SAT scores probably tend to go up also. So we're kind of looking at that linear regression, or the linear relationship between those scores. So logistic regression is different because in this case we have a dichotomous outcome. By dichotomous, we mean either like a yes, no, 0, 1, A or B, is present, is not present, alive, not alive, so the outcome is dichotomous. And so the question that we're answering here is a little bit different because we're actually looking at probabilities. So in this case, we're answering the question: as one variable of interest goes up, meaning your independent variables or your predictor variables, as it goes up, what happens to the probability of being a 1, and I put 1 in quotes here, for the dependent variable? So what happens in our probability of retaining something that we happen to be measuring? Okay, and so again, these things are, the outcome is mutually exclusive. Someone can't be both 1 and 0 at the same time. So we're just looking at, okay, this is, did they come in our store? Did they not come in our store? Do they, again, as we were saying before, are they alive? Are they dead? And so we're typically going to code that as 1 and 0. But as we're going to see here in a little bit, some of the things that we're looking at inside of Alteryx, we don't actually have to code it as a 1 and a 0 as long as there's only 2 outcomes. And I'll show you what I mean by that here after a while. Okay, so let's talk a little bit about data types. And we did this with linear regression, but we need to do this again. But in linear regression, we talked about, well, that's a typo there. In linear regression, it says your outcome must be dichotomous, but your outcome must be continuous is what that should say. Sorry about that. In logistic regression, again, your outcome variable must be a string for Alteryx. Okay, now this is weird. So because we're talking about outcomes that are 0 and 1, and I just said it has to be a string. inside of Alteryx. That's because the way that the coding is going to work inside of the Alteryx engine, which is using R for running the logistic regression, the way they're setting up, it was just easier to be able to pass a string and to let someone, code their data as yes, no, or A, B, or something like that, so that it just made more sense when the people who were coding Alteryx set it up this way. So we'll talk about that, and I'll show you if you do have data that when it comes in, it's not set up as a string. We'll show you how to set it up as a string so that your outcome will actually be recognized by Alteryx and you can actually select it. Okay. If your predictor variables are string, then Alteryx is going to dummy code them. So we can use predictor variables that are string, like if you belong to company A, B, or C, but Alteryx is going to dummy code them. I'm not going to talk a lot about that right now and what that means, because we talked about that a lot in the last training session on linear regression. But you can put string variables as predictors in here, although you wouldn't want a lot of categories. So you wouldn't want, let's say, if you put a variable in there that had, let's say, 35 different categories or something like that, would make for a really complicated model to try to interpret. So generally, it's a bad case. And generally, in any type of multiple regression, whether it be linear or logistic, it's not the greatest of ideas to have string variables as predictors. Now, in logistic, we are going to look at it as the outcome. But for predictor variables, it's generally a bad idea. And we don't want to go too deep into statistical theory on this, but let's just leave that one there. So how's Alteryx going to handle your data type? So if your dependent variable is something other than 0 or 1, Alteryx is going to assign it to a 0 and or a 1 in alphanumeric order. So again, let's suppose that your dependent variable is coded A and B. Well, because it's going to do it in alphanumeric order, A will be the 0 and B will be the 1 in your outcome. Okay, so, and if you coded it B and C, well, then of course B would be the 0 and then C would be the 1. Or if you coded it no or yes, then no would be the 0 because N comes before Y, and yes would be 1. Or if your outcome variable coded like Bob and Dan, what's the probability of being Dan? Is what we would be looking at. So Bob would be coded to 0 and Dan would be coded to 1. Okay, now here's the part where we do need to talk statistical theory just for a second. In logistic regression, what we're going to compute is the probability that you are a 1. So in these three cases down below, we're going to compute the probability that in the first case that you are a B, the probability that you are a yes, or the probability that you are a Dan. So in these three cases. So when we're going to look at the probabilities in the output, when we're going to score new data, that's what we're necessarily looking at, is the probability that you retain something that we're trying to model, or some attribute or some trait that we're trying to model. Okay. All right, so again, as Rachel said, here are two places that you can get the data. This is done as much for people who will be watching this afterwards. So you can either get this out of my GitHub account under the Alteryx Training Logistic, or all data files for all sessions are going to be up on our Teknion USA website. And so you'll be able to download them from there. Okay, all right, so why don't we fire up Alteryx, and then in firing up Alteryx, we'll, sorry. Okay, so we're going to look at this data, and I have a data set called Logistic Train, and that's what I'm looking at right now. And so let's look at everything that's in here. So we have a case number for a data file, for each case in our data file, and then we have this first variable that this is called in-hospital event. And what this is this is a variable that is whether or not someone inside a hospital, and this is all fake data, I made it up myself, so nothing, we're not violating any HIPAA laws or anything like that. This variable, what this models is whether or not someone, while they were in the hospital, they had an event that we would categorize as a significant event, such as, let's say, while they're in the hospital, they had a stroke, or they had something with their heart, or they had a serious medical condition while they were in the care of the hospital. Okay, so this is all kind of fake hospital data. And then the second one is whether or not they had been they got readmitted, or they were readmitted after the fact, or after they visited this hospital. Now, the reason we're using this data set is that readmittance into hospitals is kind of a hot button right now, and so we just thought, well, we'll simulate some data around this, and so this is going to be our outcome variable that we care about a whole bunch, is whether or not someone is readmitted into the hospital after we released them. So in this case, you can see that I have, probably about 44 people who were not readmitted, and I have 38 people who were readmitted. So this data set kind of small, 82 cases, but still it's an interesting data set for us to look at. Okay, so we're gonna try to model in our outcome the probability that someone will be readmitted to our hospital based on some information that we have about them. Okay, so we have whether or not they had an in-hospital event, and then we have this. This is a knowledge test that we've given everyone. Okay. And this knowledge test really is about, like, how much do you know about the reason that you're in the hospital and, like, the disease that you may be treated for, or the condition that you're treated for. Okay. We have another one that is previous admissions, like how many times have they been admitted to our hospital before this? And then the final one out here is something called comorbidities. And comorbidities are significant medical conditions that someone has along with the thing that they're being treated for. So this would be like if someone's coming in with a heart condition and they have, in addition to the heart condition, they have, let's say, diabetes, and they are obese, and maybe they've also had a stroke. Okay, so that person would have like 3 comorbidities, or really, bad conditions that we would want to consider. Okay, all right. So what we're going to do again is we're going to go ahead and pull in our logistic regression tool here, and we're going to connect that up to our data set. And then I've also got a scoring data set that we'll mess with that a little bit later. I'm going to go ahead and add all my browses, and then let's set this model up. Okay, so first we'll notice the only variable that we can see in when we're selecting the target variable is this readmit. Let's talk about why that is for just a second. I'm going to pull a select tool down here, and you can see from the select tool this readmit variable is one that is listed as the only one that's a string. Okay, and we know that one's a 0 or 1. So, and let's suppose we were to change this to a double, or even just a byte, because it's 0, 1, we could put it in a byte format. Now, when we trying to run our, we'll actually see that there's, although that is actually done there, that's well, that's not possible to pull that in. Okay, so if we were to try to run this, it would actually, that readmit would actually be grayed out. I'm not sure why it's there right now, but so we need to, in here, I'm just going to delete and connect around, or we just need to make sure that the variable that's coming in is a string. So we are seeing, okay, yeah, there it is. Now we can actually select it. Okay, and I'm going to rename this. I'm going to call this first run. Sorry, outcome variable readmit. That's what we're predicting. And remember, we're predicting the probability that someone will be readmitted. Okay, I'm going to select all these. I don't need the case, and we don't want to readmit back into our data set there. So we're going to select whether or not they had an in-hospital event, their knowledge test, number of previous admissions, and then comorbidities. We have all of those set up, and then we'll go ahead and click run over here, and we'll let Alteryx do its thing. And so now here's some things we need to say about Alteryx. And again, this is a little bit complicated, but need to say it anyway. It's when we set up the model, we set it up in such a way that we're actually using what's called a Logit model. Now, there's other types of models. We can use Probit or complementary log-log. But what, again, without getting into too much statistical theory, this is actually the thing that we're predicting. We're predicting what's called a Logit. And then we transform that back into a probability afterwards, because probabilities are not on a linear scale, and Logits are more on a linear scale anyway. It's easier for us to think about it in those terms. And then we transform our Logits back into a probability in our output. So let's talk about the anchors that are coming out. This first one, this is the model that's actually coming out. That's appears, and we're going to connect to that, like if we want to score another data set. That's the first one. The second one is, this is all the information from our model run. And for those of you that are really experts in R, this is the exact type of output you would see from R that you would see. We are modeling readmit is a product of someone's in-hospital event, knowledge test, previous admissions, and then comorbidities. Okay, that's what we're looking at there. All right, so now we look at these estimates. So it looks like we have two estimates that are statistically significant, whether or not someone had an in-hospital event and their comorbidities. Those are two statistically significant predictors. And the way to think about this is, because this is positive, 0.251 for the in-hospital event, then we're saying that people who do have an in-hospital event have 2.5166 more Logits, predicted Logits, or a higher predicted Logit than does someone who does not have an in-hospital event. Now, I know that's weird to think about, because we'll be talking about probabilities, but we could do some work if we wanted to, and we could transform these into actual probabilities by doing a little math, but we're not going to this time. And this is all I want you to notice. The first thing we want to look at is it statistically significant, meaning it is a statistically significant predictor, and this value right here. So for every 1 point change in in-hospital event, this is how much the Logits go up. Logits go up 2.5 points. Now, it's hard to know what that relatively means, but for comorbidities, what it means here is that for every additional comorbidity that someone has, their predicted Logit goes up one point, just a little bit more than 1 point. So more comorbidities, the higher their predicted Logit goes up, meaning the higher the probability that they are going to be readmitted. So the two things that are driving the bus here is that if someone has an in-hospital event, and if the more comorbidities they have, the higher the probability that they're going to be readmitted into our hospital. Okay. I'm going to, again, a little bit too much to talk about statistical theory in these two lines, but I do want to talk just a second about this McFadden R squared, 0.399. You can think of that as a multiple R squared, like in regression, however, or in linear regression. However, there are some statistics that we actually care about more than we care about that McFadden R squared. Okay, and those are actually listed for us in this next tool. So we'll pull this tool up, and then we're going to talk about everything in here. All right. So the first thing I want to look at is down on the bottom here. This is called a confusion matrix. And what it is it's a matrix that says, all right, based on our model, who did we predict to be a 1 and who did we predict to be a 0? And then what was their actual score? Who was actually a 1 and who was actually a 0? Okay, so the green boxes are people that we predicted correctly. So this first one, 33 out of 82 actually were a 1 and we predicted them to be a 1. And then 34 out of 82 were actually a 0 and we predicted them to be a 0. So these greens, those are the ones that we predicted correctly based on our model. The pinks are the ones that we missed, okay? And that is reflected up here in this number right here, accuracy, 0.817. So that means in our model, we correctly classified 81 to 80, almost 82% of the people in our model. That's pretty good. That's not bad at all. And again, it kind of depends on it's relative to what you're studying. But this actually gives us some quite a bit of information. So we're getting accuracy at 0.817. That's not bad. So if our accuracy is 50% or below, then that means we're not doing any better than someone who's just throwing darts at a board and kind of picking based on the distribution. So of how many yeses and nos there are. Okay. So this is also, again, for you statistics people, this accuracy number is also called the Huberty I index. And so if you care about that, or if you see that in a study, that's all they're reporting right here is this. It's 33 plus 34, all of that divided by, so that would be what, 67 divided by the total in here, that's 82, and that would give you this this accuracy index. Okay. So this is usually the first thing I look up when I run a model is like, how good am I doing? How well am I predicting based on, based on my model? Okay. The conditional density plots, I think this is really nice feature inside of Alteryx and something they show for us. So what we have is on the y-axis here is our probability of response, so going from 0 to 1. Okay. and then how much someone having an in-hospital event actually contributes toward that probability. So in-hospital event, this is for each of our values. So in other words, if someone does not have an in-hospital event, then we're seeing their probability change across here. So as people do have in-hospital events, then their probabilities are actually changing based on this conditional density plot. Okay, again, we're seeing the same thing here. And what we really like to see when we're looking at variables that are really good, we really like to see either a good step like this or kind of a consistent, this is that comorbidities, a consistent ramp down. What we don't like to see, and this is a good indication of a variable that's not doing very well, this knowledge test has a whole bunch of jumps based on how much knowledge you have, and so it's rather wavy. That would be a good example of a variable that's not doing very well. And then we're also variables that have, let's say, that are a continuous variable, not a 0 to 1 like in hospital event, and then they have a huge step where they just are staying right up at the top, and then they kind of conditionally start to step down across as we have more. This one, again, probably not as good of a variable, but yeah, this in-hospital event, that's a huge step. That's good for us. This is bad, that waviness. And again, also to the comorbidities, that's a good indicator, again, of a good variable. And as we saw before, yeah, the in-hospital event, that was a good predictor, statistically significant predictor, and so was the comorbidities. Okay. And then we've got some performance things in here. I'm not going to talk about these, but the ROC chart, this is kind of like an area under the curve chart. Anyway, I'm not going to talk too much about that, but just other than to say the further we get away from this diagonal line, meaning the more steep this is up in this direction, the better we're doing at modeling our data. Okay, I'm going to leave that alone. Okay, all right, so we have our data, and so we're saying, all right, I like this model, I like these 4 predictors, even though I've got 2 that aren't statistically significant. I do like them, and so I want to now score some new data. So let's suppose we've got a new data set around here that has, in this case, this one also has 82 people in it, and we want to score this. Okay, so let's talk about doing that. We're going to grab the score tool from Alteryx, pull that down. Okay, and then we've got 2 anchors here. There's a data anchor, and then there's a model anchor. So we're going to grab this O anchor coming out of the logistic regression and then plug that into the model. And then we're going to grab data from this new data set. And so what this scoring tool is doing is it's saying, all right, based on the data, the new data that we have, and you notice this new data set does not have whether or not someone is readmitted. There's no variable in there. So we're going to predict their readmission based on the results of, or the weights coming out of this logistic regression model. And so I'm going to fill out one thing over here. This is the new field to name. So we're going to call this pred readmit. Okay. So what Alteryx is going to do now when we run this model is it's going to produce the predictions for this data set. So it's going to predict how probable are they to be readmitted based on the weights from this model, given their data set, and then we'll run this. It'll take just a second to run, and then we'll look at our predictions afterwards, and then we'll have some more where we're going to kind of need to talk about a few things and decisions that we're going to need to make as a result of that. Okay. So this is almost done running, and as soon as it is, we'll look at the output here. Okay. So we have 2 new variables. And what these variables are is this is the predicted readmit. This first one is the probability that this person is a 0, and then the probability that they are a 1. Now, one of the things that I would like in the scoring tool that isn't here is actually getting the predicted logit, because sometimes that's we may want to do something with that afterwards. But in the case of Alteryx, they're just giving us the predicted probability. So another way to think about this is this person, based on the weights from the other model, this first person, case number 210, the probability that they're a 0 is 96.6%, and the probability that they're a 1 is 0.03. Now, you may be thinking to yourself, hey, it would be really nice if we actually just knew which one's a 0 and which one's a 1. We can absolutely do that. So we'll actually pull out a formula tool and we'll connect it in here. And here's where we have to make a decision. We're going to make a new variable for ourselves. We'll call it readmit 0, 1. Okay. And we'll use a if-then statement. So we'll say if, and then we're going to pull in this probability of readmit for a 1. So we'll say if that is greater than 0.5, then they get a score of 1, else they get a score of 0, and we'll just put our end if in here. Okay, now why did I say that we need to make some decisions here? Okay, so in our case, what we think is that if someone has a probability of being a 1 of greater than 50%, then we may say, all right, that's somebody that we'd say, all right, they have a higher probability of being a 1. That's what we want to look at. Okay, so we want to call them a 1 if they're above a 0.5. Now, let's suppose we're doing cancer research and we're trying to, based on a number of factors, we're trying to predict the probability that they could have cancer. We're gonna assign 0s and 1s based on that. In that case, I'm probably not going to use this 0.5 record because we may not know near as much about cancer research. We may jump that down to, let's say, 0.15 or 0.2 because we want to screen for ourselves. So we want to say, all right, anyone who has even a mild probability of cancer, we probably need to check that out. And so we want to create decisions based on that. So I'm putting a 0.5 in here because this is hospital readmits, but this is where your theory or your statistical theory is really going to drive the bus on the how much do you think that a person what is the criteria, what number here do you want to put in there to say, all right, this one we're going to call a 1, this one we're going to call a 0. Okay. So in this case, I'm just going to put it at 0.5 and we'll call it good, and then we'll go ahead and we'll run this now. And we'll see what our results look like after all of this is done, and we'll make sure that we actually did things correctly. So as this is running, all right. So let's click on that output anchor, and we'll see. All right, make sure we did everything right. So the probability that first person to be in a 0 is really high, 96%, and we're saying, yeah, indeed, they're a 0. And then the next one is, and this is an interesting one because the next one is really kind of 50-50, that we're saying their probability of readmit is 0, which is the same as the person above them, but really it's kind of a toss-up. We're not sure on that one. As opposed to this third person, their probability of being readmitted is really, really high. You see that 93% probability, and so we're coding them as a 1. Okay. So what we could then do is take this data, and so let's suppose that someone, our healthcare professionals who are checking people out of the hospital, they may have a person who's coming through, and then they're wanting to know, hey, what's the probability that we're going to readmit? Because in hospitals, the amount that we're given by the government is also somewhat dependent on our level of readmits. And they don't like readmits, and so it's worth it for us to keep someone there if they have a high probability of being readmitted. So we may build a tool and say, let's say inside a Tableau, where now someone can enter in the information for a single person and then can use our model to actually score them and get the results back on, yeah, okay, here's the probability of that. And in that case, we may actually want to just report this probability here so that they can make their own judgment call, or maybe a 0 or 1. Okay, so let's talk for a second about when we might want to use this, other use cases. So that may make sense that we want to build a model where we're trying to figure out what someone's probability of default, given we're trying to give them a loan. So we may have factors in there like the loan amount, the rate, the term, how much money they make, what their FICO score is, things like that, in order to determine whether or not we should lend that person a loan. So that's a kind of a yes or no decision, but the probability they're going to be defaulting, or really just anything that we can dichotomize. And we can think about, okay, yes or no, this is going to happen, or this isn't going to happen. Okay. All right, so that's a data set. And that's logistic regression. But I did want to show you a couple of things about Alteryx also, that now that we've seen this, we can actually talk about. So if we look at the output again, I'm going to pull this back up because there's something in here that's actually I think will be really interesting to you. But we needed to see that before. So, oh, not there. There, sorry. Oh, okay. This value right here, this optimal probability cutoff. This is 0.486. Okay. What Alteryx is doing is it's telling you the place at which it is making the decision for you about when someone is scored as a 1 and when someone is scored as a 0. Okay. And they're saying in this case, because of some, again, we're getting to statistical theory here, but they're saying in this case, it makes sense for the cutoff for someone being a 1 to be at the, the probability being 1 at 0.486. And whereas opposed to when I was actually making, this thing down here, I was putting it at 0.5. What Alteryx is telling you is that really it should be probably about 0.486. Okay. And let me show you why this is important, because you may think, all right, I've got this information coming out of here, and as a result of the data coming out, let's suppose instead of scoring this new data, I know this will sound weird, but let's actually score our original data set. And then we put in here the probability of being a 0.05. So let's run, or 0.5. Let me run this again, and I'll show you kind of why this is important. We're going to create our own little confusion matrix, if you will, and then talk about, oh, I must have put in something incorrect. Hang on. I pulled the wrong place for the data stream. Sorry about that. Let me actually pull it from the actual data. There we go. That should work. My apologies there. So when we're going to pull this in, so this is kind of funny that we're running our data and then we're scoring the same data set because we want to reproduce that confusion matrix that was before. And so I'll show you a little bit on how we did that, and then we'll go from there. So what I'm going to do is add a transform tool here that's a summarize. Actually, before I do that, I'm going to do a select just to make things a whole much easier for us. And all we're going to keep is whether or not they're readmitted, and then this 0, 1 that we have on there. Okay. And then in the select tool, what we're going to do is we're going to group by readmit, and then also group by readmit 01, and then we'll just do a count of that. Okay. And just in case we need it, I'm going to go ahead and cache this from that point forward, just in case we want to play with it some more. As this is running through, the thing I'm wanting to show you is that if you remember our predicted or our Huber DI index, or our precision that we were looking at before was 81.7%. But let's look now. Okay, so here's the someone who was a 0 and we scored them as a 0. There's 34 of them. Someone who was a 0 and we scored them 1. There's 10 of them. Someone who was a 1 and we scored them a 0. There's 8 of them. And then here's someone who was a 1 and we scored them a 1. There's 30 of them. Okay, so in this case, what we're looking at here is these numbers are exactly the same numbers as we saw from the output of our regression to our logistic regression. And these are the numbers that we would actually use in order to compute that Huber DI index. And so in a pinch, we could actually, you can do this for your own data set, but again, Alteryx is actually just makes things a whole bunch easier for you by go ahead and computing this for you. But I just wanted to show you that's how we would get to that spot. Okay. All right. So I realize this has been a whole lot like drinking from a fire hose so far, but let's look at one more thing and then we'll get to questions. Okay. So let's suppose we like this. And so we like our model. I'll tell you what, I'm going to take that off of there just so I can get rid of that cache now. Because I did change my mind on that. And let's say we want to run a different logistic regression. We'll get rid of all this. We're thinking about it and we're going, it doesn't make sense. I need to be a little more parsimonious. And so I want to know, what if instead we'll call this one call this logistic2 or log2. We still want that readmit, but in this case, we only care about predicting it with the in-hospital event and the comorbidities, because before those were the only things we really cared about. So let's add all the browsers afterwards. I tell you what, I will put this one into a container, and we'll close that out just so that it doesn't take as long to run. And then we'll go ahead and run this. Okay. Now remember too, our precision in our old one was 81.7% or 82%. That's how good we were doing. So let's look at this new one and let's see, you know what, if we only use 2 variables, how well would we do? And again, it's just making things more parsimonious. This is not bad. So look at our accuracy there, 0.793. So we lost 2/100ths of a point of accuracy, which is really like one person that we're now incorrectly specifying. We just lost 1. Our accuracy went up. Okay. So this may be a case where we go, you know what? In this instance, I think it makes more sense for us to actually drop those 2 variables, because again, if you're like me, Occam's razors that drives the bus on us, that we would say, yeah, the simpler one is usually better. So we're only grading about 2/100ths of a point, or 1 more person that we're correctly specifying, if we include those other 2 variables. I'm all for simpler models. Only have 2 variables here, in-hospital event and comorbidities, and you know what? This may be the one that I want to go against, and so I may just want to choose this one. So again, that's where we're starting to do a lot with playing with the models and try to figure out which one we like the best, and then so we can make the best decision. Okay, so that's a lot of thinking about prediction and logistic regression. And so I tell you what we're going to do is I'm going to invite Rachel back in to ask some questions, and we'll go through as many of those as we can in the next few minutes. Okay.
Sure. So our first question is, can we use logistic regression to predict more than 2 outputs on multiple categories?
Okay, so that's a great question. So can we use logistic regression to predict more than 2 output or multiple categories? So no. However, we can set up a series of, so we have like, 1 versus 2, and then 2 versus 3, and then 1 versus 3. But in a case like that, you're probably not going to want to predict multiple categories. So it may make more sense to do more of a decision tree type setup. But for logistic regression, we can only be 2 outputs. I mean, that's the only output we can. So we're probably going to move to a decision tree type scenario when we have more than 1 outcome category. So great question. Great question.
Another question is, what is the difference between a z-value and a t-test?
Okay, so a z-value and a t-test. So in a t-test is just a special case of ANOVA. And what it is we're looking for 2 different, we're looking for the probability, or not the probability, we're looking at 2 means. Okay, so we're saying like the mean of group A and the mean of group B tested against each other. That's a t-test. And so we're not actually predicting whether or not someone is in group A or group B. We're just saying like, okay, we have IQ scores for students in group A and we have IQ scores for students in group B. And a t-test would check to see, is the average IQ score for group A different than the average IQ score for group B? That's all a t-test does. And so there's no prediction there. There's just testing for the differences of means. And so now a z-test is going to be a bit different in that we're not actually looking at means, and we're using a little bit of different scores. And so I'm a little bit confused on the question. So maybe follow that up with with another question on what you're meaning there. But Z is usually looking at some sort of standardized score and weighting that. And so I'm not quite sure of the question, but as far as a t-test and logistic regression, one of them is just testing for differences of means, and one of them is actually doing prediction. Okay, good question.
Sure. For those of us that are not statisticians, is there anything in the software that will flag you if you say you don't have a large enough sample size?
Yeah, so it'll fail. So that's a great question. So the good part about the way Alteryx interacts with the R engine is that if you don't have enough variability, or if you don't have enough degrees of freedom, meaning you don't have enough people in your analysis, then what will happen is generally the engine will just lock up. And so you'll get all these red error messages that mean nothing at all. Like they're really odd messages. And then when you search for the messages, most of the time people will say, it's probably just you don't have enough people in your study. So but there is the question of that. That's really kind of a weighted question there. So sometimes it will just fail, but there are other times that you're going, okay, there aren't enough pieces of data in our analysis to actually get to the point where we would say, all right, we have enough people that our answers are robust. And so that's where we would look at that confusion matrix, and the number of people that we're correctly classifying. That's when we would start to care about that. So we definitely want we want that number to be relatively high, to where we're correctly classifying all those people. So I think that's a good question, and something we definitely need to consider when you're in there. Now, there are good rules of thumb. There's a great book by a guy named Cohen called Power Analysis in the Statistical Sciences, or the Behavioral Sciences, or I think it's Behavioral Sciences. But there are a lot of charts on how many people do you need in your study based on what you expect. So your key word on this is power analysis. And so if you're wanting to know ahead of time, like how many observations, I want to do this type of analysis, how many observations do I need? All you really need to do is Google power analysis and then logistic regression, or power analysis and linear regression, or power analysis and whatever it is you're working on, ANOVA. And then that will give you an idea of how many people you are going to need. And there's lots and lots and lots of information out there. In fact, I've written quite a bit about this also. And actually one article that I wrote, well, it's been 15, 20 years though, ago, it's probably about 15 years ago, an article that I wrote, actually it generated a lot of discussion, and there was a whole edition of a journal that was dedicated to this effect. It was called effect size reporting, and that we use that to determine how we get our power. And so there's not much controversy around this. I mean, it's pretty solid science, but there is a lot of debate on how we interpret some of these things. So great question.
Does anything change if you normalize the comorbidities to be between 0 and 1? Basically, will the output change for the better if we normalize the data? Okay,
that's a good question. So if we just scale it between 0 and 1, then the only thing that will change, like our outcome won't change. It's just the weight that would be associated with that variable. So let me show you what I mean. If we change the scale, then this number here will just change relative to how much we change. So if we bind comorbidities to be between 0 and 1 instead of 0 and what I think 6 is the most comorbidities, then all that we would be doing would be just like dividing all the comorbidities by 6 to put it on the same scale between 0 and 1. It would be the same as if we just divided that by 6. Now, there's a good question in there, and that you said if we normalize, I think was the word. We'll go back to that question. Yeah, and now if we normalize the data, now that is a different question. So if we apply some sort of norming algorithm to this, or maybe some transformation to this that's non-linear, then yes, it will have a pretty significant effect on this. But as long as we're just saying, hey, I want the scale of comorbidities to be between 0 and 1, and so we're dividing by 6, and now it's between 0 and 1. So the person who had 6 comorbidities is now a perfect 1, and then all the way down. Then all it's going to do is you could just take this number here and divide it by 6, and that would be the same. Okay, great question. Yeah.
Is there a difference or is there a preference to what is a better model scoring method, such as the confusion matrix versus R-squared? Are there cases when one would be more valuable than the other?
Great question. So the R-squared metrics, I don't generally use them much in logistic regression because they're they're not a direct corollary to an R-squared metric that's in linear regression. And so they're kind of an approximation to what a linear regression R-squared would think about, but we're not actually modeling in R-squared and linear regression, we're modeling the percent variance. So we're explaining it's a bit more complicated in logistic regression. And so the only reason I prefer like looking at a confusion matrix is that confusion matrix is, I can easily explain that to a CEO, right? I can say, of the people, there's the correct percentage that we're classifying. And so that's why I prefer that, as opposed to because now to give them the R-squared, like the McFadden's, in order to explain that, it's really difficult. It's not the same as, it's easier to explain in linear regression, okay, that these variables, my predictor variables, are explaining 75% of what's going on in my outcome variable. That's easy to explain. But when you're doing it in logistic regression, it's not that straightforward. So I generally prefer that to use something like a confusion matrix and the Huber-DI index. Great question.
What's the difference between a Logit model and a
Probit model? Yeah, so great question. And so all it is they're really kind of the same flavors of ice cream with maybe just a little bit different sauce on them. And so really it's about the outcome variable that you're predicting. And so in the case of a Logit model, you're actually predicting a Logit. And then in the case of a Probit model, you're actually transforming the data to predict a Probit. And then I think the Logit for me is, again, we're getting into statistical theory here, but I think for me, the Logit one is the one you're going to use 99 times out of 100. For practical purposes, the only time you would use a Probit model is if someone said, hey, we're expecting the distribution of our scores to be really odd, and then the way the relationship between the zeros and ones are, then you might want to use a Probit. But it's probably a little more than we have time to go into. Again, when I'm teaching class, I might take 2 hours to explain this to students, but that's after they have a really good understanding of what a Logit model is, and then we talk about Probit models. Okay, so yeah, let's just say 99% of the time stick with a Logit model. It's a good question, but deeper than we're going to have time for today. I apologize.
And so I think we only have time for one more question, and that is, what is the size limit of training data?
Okay, so that's a good question, as I was in before. Part of it is, it was asked before, part of it depends on how many predictor variables you have. So if you're going to throw 15, 20 variables into here, you better have a big data set size. But it also relates to how much power you expect. And so if you expect that you have something that's pretty easy to predict, like whether or not someone is going to cross the street when the light turns green. That's pretty easy to predict, okay? Or whether they're going to try to cross while there's not a green light, okay? So pretty easy to predict because most of the people are choosing green light anyway. When that's the case, you expect it's going to be pretty easy to predict and you don't need near as many people. It's when you're trying to predict something that's really hard that you need as many cases as you can get. And you'll find also too, statisticians and data scientists, we love data. More is better, always better. There's never a case where we would turn down data. We just wouldn't do it. So giving you a hard and fast number is really kind of hard to do because a lot of it depends on how much data, how difficult is it to predict the thing that you're trying to predict, and how many variables are you trying to use to do that. And so on the training data, that's, if we're following the central limit theorem, then we would say that, at least 30, but now that we're in logistic regression, that's not a normal distribution, so it's probably going to be a bit more, but it really kind of depends on so many things. So I would hesitate to say, start at 200, because I can think of cases where, 75 is plenty. And so I think also the other thing to do is, this is where, when you're doing your research before you start to do a logistic model, you try to find people who've done things that are really similar to what you've done before. And how many people did they use, and then how did they notice, was their data really volatile? And that'll give you an idea on whether or not you can use less or more. But it's hard to say, all right, in a training data set, you need 200 people. It's really difficult to say that. Sorry. That's a really long, terrible answer, but that's kind of all I have on that. So, all right. Again, thank y'all all for your time. So next week, I believe we have Dina Sanchez up. And so if you've not met Dina before, she's outstanding and should do a really good job. And I think you'll look forward to it. So I'll turn it back over to Rachel here.
Sure. So last reminder, these are our upcoming webinars. As Kyle just mentioned, Dina will be covering data prep and blending moving forward. And today's webinar was recorded. The link will be sent out via email within the next few days. So yeah, thanks for joining us today. Be sure to reach out to us if you have any questions. You can reach out to us on our social medias, or Kyle's contact information will also be linked with the webinar recordings.
All right, thank y'all so much.